Good afternoon, everyone. My name is Xing Guoren from School of Physics. I will chair this session. It's a great honor and pleasure to welcome Professor Matthias Schäfer to give this talk. This talk, as you have heard, actually it's this is the Sophie Forum of Great Minds. Actually, supporting this forum. Actually, we have you a certificate to present to Professor Matthias Schäfer. Yeah, so we present this to you.
Okay. Thank you.
Take picture. You take picture.
Okay. That. What? Okay. Good.
Okay.
Thank you.
Yeah. Now let me introduce a little bit about Professor Schäfer. Professor Schäfer obtained his PhD from Technical University of Berlin in 1978. He was then a scientific staff member of Physics Technische Bundesanstalt from 1978 to 1987. And actually, during this time, he spent a year at IBM Yorktown Heights in US. And in 1988, he became the founding director of the theory department of the Fritz Haber Institute at the age of 36. And he has been there since then. So he's the honorary professor at all three universities in Berlin. And in 2004, the University of California, Santa Barbara, appointed him as distinguished visiting professor for computational materials science and engineering. Professor Schäfer's research focused on understanding fundamental aspects of physics and chemical properties of surfaces, interfaces, clusters, and all kinds of systems. Actually, he works on a lot of different topics. And recently, he's engaged in developing theoretical methods treating exciticities and electron collisions, as well as computer codes to perform large-scale electronic structure calculations on high-performance computers. In the recent year, he developed a neural network and a complex sensing method to identify structure and patterns in big data of material and to create maps of material. I think this is the topic mainly for today. I would like to also mention that Professor Schäfer got several prestigious honors, including Fellow of American Physical Society and the Max Planck Research Award, and the Max Born Prize, and the Ernst Mach Prize. I think just name a few. And I would like also to mention actually, Professor Schäfer in his department hosts a lot of Chinese students. I think so far at least more than 50 Chinese students, Chinese postdoc students have worked with him in his department. And nowadays, most of them are in China. In a sense, he also has a greater influence, greater impact on the Chinese and electronic structure community. Now, and it's great pleasure to have you here today and give this very talk. Now the time is yours. Let's welcome.
Okay, thank you very much. It's really a great pleasure being here, having a lot of good friends and collaborators. Now, So the title of the talk, which you have seen, Making the Data Revolution Happen, deals with what is also nowadays called big data, an issue which more and more scientists are facing. Some are facing it already now, but others will realize that soon, that if you do experimental physics or theoretical physics, one creates really a lot of data. This causes some challenges and problems, but I think what I want to emphasize is that this does not really cause problems and challenges, but there is a big chance of a new type of physics you can do with this. And there is, in fact, what I call, or actually many people now call, a new materials research paradigm. A paradigm means it's not just a new equation or something, it's a new line of thinking. It's very often people think actually a new paradigm means the old way of thinking can be forgotten. That's not really true. It's a new type of thinking, very different, orthogonally, basically, to everything which was there before, but it's complementary. It adds to the other ones. And I will give a little bit of history of this during my talk. And you see that the subtitle somewhat is turning data from information from computational material science into knowledge by artificial intelligence. I concentrate on computational material science, but the methods, the ideas which I present are equally valid also for experimental science, and we can discuss that also later because there are certainly also some additional challenges if you go to experimental science. But I mean, I'm a computational scientist, and there I know where the problems are, and that's why I can handle them better than experimental sciences. Now, I was told that actually some people may not really coming from material science, and so let me very briefly tell you why is material science an interesting and very fashionable and very important field. So why is it important? And the simple answer is somewhat here below. Materials are an essential foundation of the prosperity and our lifestyle. So basically nearly every new product, every new smartphone or whatever you have really is based on materials which we did not know 20 years ago. Also catalysts in surface science and whatever. These are materials which are only produced recently and which show a new function which we didn't have there before. And this is in fact where the NOMAD, which stands for Novel Materials Discovery Laboratory, which is a European Center of Excellence, is coming in, and that is the center or the focus of this NOMAD Center of Excellence. And what I'm telling you is work which has been created in the Center of Excellence over the last years. So one more slide on why materials are important, because this has been realized also by someone else, and that is Obama, who 7 years ago started what he called the Materials Genome Initiative. What is often forgotten is the reason for global competitiveness. And here are some words of his: to help business discover, develop, and deploy new materials. Twice as fast, we are launching what we call the Materials Genome Initiative. The invention of silicon circuits and lithium-ion batteries made computers and iPods and iPads possible, but it took years to get these technologies from the drawing board to the marketplace. We can do it faster. And so that is somewhat the economic reason why people are looking into this. As a scientist, in fact, it's also in having a better understanding from materials is certainly an issue by itself. That everything that you find will be used at some point in a good or a bad way is something you have also to realize, and it's actually also fine if it's done in the good way. This Obama initiative has this name. I mean, there is no genome. That was just actually a name which was invented by the White House because they felt to sell this thing to the public, they need a fancy name. And I know that now in China, you somewhat took the same name from the Americans. You shouldn't take everything from the Americans. But in this case, actually, you took the same name from the Americans, Materials Genome, and you have an institute here and there, and there are really foundations of this institute at many, many places in China. I know some in Shanghai. I know actually in Beijing. There's something planned and will be there in 1 or 2 years and so on. There was a nice booklet coming with this, which is, in fact, even worth reading, although it came from the White House, the Materials Genome Initiative description, why this is an interesting and important thing. Very short for my talk, let me just summarize. The idea is compute or measure the basic properties, and that is what we call genes, of many, and we mean, it was meant 10,000 materials, and to disseminate that information to the materials community to enable rapid searches and design. So I will, as I said before, concentrate on compute, but you can do, as I said, use the same ideas with experimental data. And of course, what is said here also, you should do this for 10,000 materials, and then you can simply search if what you're interested is there already. That was the idea 7 years ago. We, in this talk, will actually go beyond that, because what we realize is just really calculating and searching is not good enough. We need artificial intelligence, and let me go through this now historically. Why is this a new paradigm? So the history of paradigms in material science and engineering. What paradigms do we know already, and why are we facing or shaping at the moment even a new paradigm? So basically science started, I would say, in the Stone Age, or maybe in the transition from the Stone Age to the Copper Age to the Bronze Age. So as I said, science started in the transition from the Stone Age to the Copper Age when people discovered what actually nowadays is called metallurgy. And of course the main equipment they had in this time was fire. I think this was actually the foundation of experimental science, which is still actually the most important one nowadays, but of course we don't have fire, we have more modern ways of fire, which I would say is maybe a free electron laser, where you can watch how electrons really form a chemical bond and how a bond is broken. Then, in something like 1590, and 1600 up to 1660, 70, it started what is now called theoretical science. People like Tycho Brahe, Johannes Kepler, Galileo Galilei, and then in particular I would say Newton and Leibniz, they concluded that what happens in nature can be described by analytic equations. And Newton and Leibniz were the people who actually introduced the differential equations. There was no differential in mathematics before. And so that came in around 1600, 1650, and that is theoretical science, a complete new paradigm in addition to the experimental science. And we know, and you already know, the classical mechanics, electrodynamics, and so on. I symbolize that by the time-dependent Schrödinger equation, because this is what I'm solving with my group, but you can actually symbolize it by anything else. Again, some years later, in 1950, because there were computers, people realized that you can do a lot more than just really building an equation, because the weak thing with these equations is that it's nice to have these equations, but you cannot really solve them. They are too complicated to be solved for systems which have more than 1, 2, 3, 4 particles. And so what came in 1950 was people like J.C. Slater designed a Hartree-Fock theory to make a local approximation, including correlations to some extent. And then Metropolis et al. Introduced Monte Carlo methods. Alder and Raman in 56 introduced molecular dynamics, and then in 64 Hohenberg and Kohn introduced density functional theory. That is solving now the equations which we have, but solving them numerically so that you can use the computer somewhat as a substitute to experiments, and you get results which you then have to analyze in a very similar way as an experimentalist would analyze their results. Now, since something like 2007, 2010, we have this fourth paradigm, which I mentioned before, which is called big data-driven science. That means even if you don't really know what is going on, you can look at data and you may, if you have the right tools, find patterns. You find structure in the data. And then from the structure you may think actually you find correlations, and from these correlations you start thinking what is the reason. That idea was first phrased by Jim Gray, who was a researcher at Microsoft Research, And this was his last big thing he did. In January 11, 2007, he gave a talk on a workshop on the fourth paradigm, data-intensive discovery. That was the last thing he did because 2 weeks later he went missing on the Pacific. His colleagues have written this up 2 years later, and so that's why I think it's really the idea, finding structure in big data, structure which you could not find if you look at just small data sets. Now we somewhat added something to this, so this is somewhat the area of NOMAD, and we are in fact adding one additional component that we also say that is what we want. We want to find a structure, we want to design maps of materials, but we also realize that some of the structure, some of the physics or the science, you may not be able to describe in equations. In many things which are very important, the physics or the science is very intricate. There are many things which play together, and it's not one equation which determines that. It could be under some condition that this is important, this is this. It's a combination of quantum mechanics and statistical mechanics. And so in many, many cases, we are convinced there is no equation behind a certain behavior of a material or other things. Or also in health, actually, that's certainly true. And so we are saying finding correlations in data is a more general concept, even if there is not an equation. So detecting patterns and anomalies in big data, and of course the way to do this is artificial intelligence, and this is what I want to discuss in my talk. Now, I'm using artificial intelligence as the umbrella term, and the general thing of artificial intelligence means learning from experience. But there are two other expressions which are also used in the field, which are nearly saying the same, although a little bit different. When I started this field, I used actually big data analytics. And that's still actually, it's a very general word. Another very popular term is machine learning, which means, in fact, learning from data. Artificial intelligence is a little bit more general because you're not only learning from data, and you can, and I will show this at the very end of my talk, why I prefer the artificial intelligence, but I would say these three terms are usually used in the same general meaning of describing the field of big data and finding patterns and anomalies and structures. It's a very general, a very interdisciplinary field. You see that in chemistry, in cheminformatics, in robotics, in bioinformatics. In fact, what I will show you later comes from signal processing, from data compression techniques. There's a lot of different people in different areas who have designed methods which now are under this umbrella of artificial intelligence, which play a role and which still need to be developed and improved. More specifically, the methods we are using are neural networks, support vector machines, kernel-rich regression, compressed sensing, and I will say a little bit about these also during my talk. So big data, what are the challenges, which I mentioned in the very, very beginning? And a computer scientists usually say the challenges are labeled as the 4V. And the 4V are volume, the amount of data, variety, the heterogeneity of form and meaning of data. Right? If you don't know what the data mean, I mean, it's nice to have data, but if you don't know what the number means, it's not really very useful. And that's very often, unfortunately, the case. Velocity at which data may change or new data arrive, and veracity, the uncertainty of the data quality. When you deal with big data, you deal with all these four issues. I would say more on the technological thing, because if you don't really manage these four, then you can't really do the next step and then doing science. Now, in computational material science, we have, I would say, only two problems. One is variety, the heterogeneity, because there are different fields from chemistry to physics to material science who all speak a slightly different language. I will say something more about this. And veracity, what is the accuracy? And Chingu, who gave the introduction, is in fact also working on the veracity in the sense that our methods which we have are still approximate, and designing or deriving better methodologies in electronic structure theory is what, for example, what Chingu is doing. if you have that, then you can actually do the analytics with the data, but first you have to understand the data. And that means you can then look for the structure. So there's structure and patterns, but how to see the structure and patterns? If you just have the data, you will not see any structure. So what we want is combined in this picture here. You want to find coordinates, which in the beginning we have no idea what it is, and this is where the science is. You have coordinates, and if you have the right coordinates, then you will find a region where you find, for example, a transparent metal. You find another region where you find a sensor or a thermoelectric system. These regions may very well overlap, because a system can have both properties, but if you are able to look at data and identify the right descriptors, the x and y coordinates, at the moment, nobody knows what they are. We only know there is structure, but we don't really know in what way should we plot them. And I'll show you how to find this in a moment. This is what we want. We want to find structure and want to understand why the hell the structure comes from. So this is where Nomad started with this motivation. And here I list what in the beginning was the Nomad principles, what you should do with data, which now is called, in fact, the data principle. The first thing which we did very strongly in Nomad is saying we need extensive sharing of scientific data. The interesting thing is 3 or 4 years ago, people in my field were just doing calculations on biggest computers, be it in China, be it in Japan or USA, millions of CPU hours, and what they published were 3 numbers in some written journal. But there was much more information which is in this data. And so what we said, this is not the right thing to do. If you really want to do big data and analytics, you should give us all the information. So we need extensive sharing of scientific data. And data must be findable, accessible, interoperable, and repurposable or reusable. Repurposable means that someone has maybe done a calculation for a certain, actually everyone is doing a calculation so far for a certain purpose. That is changing a little bit now, but in the old time it was, you had for example, let's say, as people in the front here are doing catalysis or surface science. You are interested on certain catalysts, and maybe titanium dioxide is a very interesting support material for catalysis. And you do a calculation on that and you publish that. But in fact, titanium dioxide is also interesting for photovoltaics. I mean, if you do titanium dioxide with some organic molecules, you have what is called the Grätzel cell, a very interesting photovoltaic thing. You could, in principle, use the information which the guy who was interested in catalysis has obtained for that. Someone else is interested in paint. Titanium dioxide is actually the white in your toothpaste or the white in the color of your walls. And so you can, in fact, use the calculations which have been done so far for a certain purpose, but you can use, if you have all the information, for something else. But you need all the information. That way I said we need extensive sharing of scientific data. This is what we call the Nomad repository, that we really told other people you should share. Now, there is a little YouTube movie. YouTube is banned in China, as you all know. So we also put that on UQ for you guys. The idea was actually very simple, but in the beginning, in fact, it was not accepted by so many people, because many people thought, actually, why should I share my valuable data with someone else? I mean, and of course, some other felt, maybe actually, if I just publish everything, somebody will find something wrong there and then make just a living out of the mistake. So it took a little bit time that people accepted that this is really bringing science significantly forward, and now most people have in fact accepted that. And you see where Nomad now is. So 3 or 4 years ago there was basically no general sharing, and now the Nomad repository already has more than 50 million calculations, which means actually several billion of CPU hours on high performance computers. And here you see the codes which have the most upload. I mean, there are altogether 40 codes, but you see, this is a logarithmic scale, right? But you see, the biggest one are, of course, I mean, our codes like FHI Ames or Claudia Draxel's code exciting, but then VASP is certainly the leading code on this uploading scale. So people have accepted that uploading all the information is useful for science, and the reason why the VASP is so big is that our American friends, I talked about this American Genome Initiative, they were calculating like hell, because the idea was to calculate and then to look for certain things which have been calculated and which have a property. They are all using VASP, and so there is a big database by Stefano Codarolo, AFlow, Chris Wolferton has OQMD, and then I would say the leading ideas came from the Materials Project by Gerd Zeder and by Kristin Persson. They all are part of this thing in the sense they all give us their data. So NOMAD is different to what they are doing. They are only using VASP, and they are only actually having the data from a very small group of people who are all in the same contract. We are saying in NOMAD, everyone should upload, and we are just checking that this is a right file structure, that there is no misuse of uploading things. We just check with parsers that this is really the input and the output file. And as I said, by now, NOMAD, and again, this is different to anything else. We are not just giving results. We are not interested in just giving you the geometry or the energy, but we are interested in the completely full input and output files, and basically accepting all important fields. And we have more than 50 million total energy calculations. This is the structure of NOMAD, which somewhat starts with the repository, which is very useful because you can just see, you want to do a calculation, you can just look if someone else has done it already. Or you do a calculation, you find your results are different to what is published, but then you can look in the input file and you find a reason why it's different to what is published. So this is very useful for the community, but it's not really very useful for data science, because as you have seen, there were so many different computer codes, and they all speak to some extent a different language. Means energies are measured in electron volts or hartrees or kilocalories or whatever, and energy zeros are different. Even the meaning of energy in some codes is different to the meaning of energy in another code. So you cannot really, this variety problem is immense in this field. Of course, you could say I like that everyone is using the same standards, but you can wait for decades that people will actually adjust to one standard. So what we have done is we said actually we have to do the next step. We have to, actually I forgot one thing to say, I feel. I come to the next step in a moment. Let me just say, well, why is it maybe attractive to other people to use NOMAD? One thing is data are kept for at least 10 years after the last upload. So from now, because we are uploading, so we certainly guarantee that data which are uploaded there are kept for 10 years. Which is nice, because and honestly this was the motivation of NOMAD, which came from Claudia Draxel and myself 6-7 years ago, was very egoistic, because when a PhD student or a postdoc had left, 2 years later I would not find the input and output files anymore. So that was the original motivation, and now we're actually giving the service to anyone else, and we keep the data there and you find what you have done or what your students have done. Open access, but we also understand, because some people said, no, actually I don't really want to give my data because that could be a gold mine and someone else is then keeping it. But most of the time this gold mine, no one, if this person is not working anymore, then you can also give it to anyone else. But we accept that people want to delay, and so we accept that people maybe not having it open access immediately. We accept a delay of up to 3 years. So if you don't really use your data for 3 years, you're probably not using it anyhow anymore. So what I'm giving here with 50 million is actually the open access data. So we don't really look at the non-open access data. They are really even on a different hard disk. And then we provide DOIs, so digital object identifiers. That means data are citable. So when you publish, you give a DOI so that the person who's interested in all the details can just go from the publication directly to the input and the output file. And I said actually there are 40 important codes which are in the field. They are all dealt with in NOMAD. The heterogeneity could hardly be worse. That is the energies and whatever I mentioned before. So the repository, the raw data is important, but not really for the science I would like to do in big data science. So the next thing is having them in a normalized way, and as people will not really agree to one standard, we felt we have to build a converter. And that means we have to build a conversion layer. That sounds very simple, right? Just make a conversion, but in fact, everyone who writes a conversion has to understand the code and the output in detail. So this was 20 people working for 1 year. So it's not really a small thing. It's really a lot of work in doing it, but now it's done that we have the archive, which is the normalized data. Looking at the data is now enabled by an encyclopedia, where on the website, you basically call this thing up and you say, I want a specific heat of this material. So that is then used as usually we do science. You look for special systems with a certain band gap and so on. That is what the encyclopedia is doing. But then also, the archive is serving the data analytics. And I give you some examples of the data analytics, namely looking for structure in data in getting new insight. And of course, visualization, I should also mention, which is fun because we have also a virtual reality environment. So as I say, with your virtual reality glasses, you can go into the crystal. You are the electrons and you look where the hole is, if it's behind you or somewhere. So it gives you some feeling, but honestly, as a theoretician, you have this feeling before. But it's actually fun to have this in being part of the crystal yourself. So this is actually where we are, and this is what we are dealing with, the variety which I mentioned. We have these conversion layers, but now very briefly about veracity, but there I'm actually very short. Veracity, that means how do we know how accurate the different computer codes are? One has to say this is something where chemistry has done a lot of work already. Material science is very, very late on this. It only came 2 years ago that material science was looking in the different codes to check if these different codes are really calculating the same number. And this is actually a paper published in 2016, Reproducibility and Density Function Theory Calculations, a paper which was managed by Legegere and Stéphane Cotonnier. Legegere was a PhD student, now he has a PhD, and this was a supervisor. And 17 different codes were actually part of it to check if they get the same result. So what results they looked at? They looked at the cohesive energy. So the energy which holds the crystal together. You have a crystal, and you ask yourself, what happens, or how much energy do I need to press this thing together? Or actually, in principle, in theory, you can also expand it in all the directions. And this is a curve which looks like the blue one here, the lowest one, or the red one. And if you plot this curve energy as a function of volume of the crystal, different codes have different values. There's a difference between different codes. And evaluating this code with a plus minus 6% of compression or expansion, you get these two codes, and then the differences which you see here in gray is called the delta value. And that measures how good these codes agree. This was done for 71 elemental solids, and these are the results. Some of the top arranged according to the delta values. There are 3 codes which stick out as they have a delta value which is essentially indistinguishable. So by definition, that the Wien code has 0 is just a choice of the authors. So they said, let's take this as a definition, as the most standard code. It's also actually the most slowest one, probably, actually the most expensive one. And then let's look actually how the other ones are. And the next ones, which are really indistinguishable, you would say, is this FHR Ames code, which also Chingu Ren is using and developing, and the exciting code by Claudia Draxl. But then the other ones coming here are nearly the same. So the interesting thing is that in the beginning, when we started this thing, the codes were not actually all giving the same results. By doing this comparison, people found some bugs. And so what you see in the publication is, of course, after the bugs have been corrected. So there's really an evolution in this whole thing. Now, after this evolution, these are the numbers, one can say that most codes which are used are essentially giving the same results. If you have a delta value of smaller than 0.5, you would say the agreement is perfect. But in fact, there are still some codes which have a delta value of 10, depending really on additional approximations, which are somewhat hidden in these codes, which one should be worried about. But this is the type of test one needs to do. This has been only done here for solids. We have to do it now for surfaces and defects and other systems. So there's much more to do, but we are working on this veracity issue in the community very, very hard. So let me come then to the big data analytics, which is what really interests me most, and where I see a lot of new ideas which are needed. So what is big data analytics in a very simple way, or what is machine learning or statistical learning? And I just summarize that here with an easy but actually mostly used approach, which is called the kernel-rich regression. The kernel-rich regression in some way is an interpolation. So you have data points and you ask, actually, how can I interpolate these data points in a reasonable way? So you have data points which I call property P for a certain measurement or experiment or theory I. So this could be, say, the energy, or let's say the band gap of a certain material. And I write this band gap of a certain material with all the information I have from the other materials as a sum with a coefficient, and then a so-called kernel, which depends on the descriptive parameters of the others. I need to say what systems are these. I mean, how to describe that. I can say this is actually silicon, this is diamond, this is this, and this is this, but I need more details about the description to have a meaningful interpolation. The set of descriptive parameters is where the science is. That was, if you remember, I said there is in principle a map, there's structure, but we don't know in fact what the descriptive parameters are. Let's assume we would know them. Then you can write a kernel, which can be either very simple, a product of two things, or it could be a polynomial. Most people are using Gaussians. So having a Gaussian means you write your quantity as a sum over Gaussians. In the old time, when I was a PhD student, we were fitting experimental data with Gaussians and getting a good result. Now, in fact, we are not using 5 Gaussians. So let's say you have 1,000 data points, you use 1,000 Gaussians. Now, of course, the fit must work. If you have 1,000 data points, 1,000 Gaussians, and 1,000 coefficients to determine, that will work. The question is still, is it a good interpolation that your system in between is working very well? The message in machine learning is, if you have more data, this equation will get better and better. The question always is, if I do this, do I really learn something from this? I'm just doing a fitting in a mathematical way, but what is it what I have from this? Or do we ever have enough data? We know that with big data you could do this, but what is really big? Now, one thing I will also emphasize at the very end is this general statement, more data means a better representation, which looks very plausible, I think is not correct for material science. And the reason is, and I say this already here, but I say it again later, in material science we have different subgroups. We have transition metals, or we have semiconductors, or we have systems which have certain chemical bonding. And just fitting them all with the same type of approach will not help us very much. Also knowing that at the end, when we are looking for a new material, let's say you're looking for, in catalysis, a better catalyst for ammonia synthesis, ammonia which you need for fertilizer, for example. The catalyst which does this is iron-based. You can add more and more and more information. If you don't have the iron information, you will not find that. So we have subgroups in material science, and in the subgroups we don't have really big data. To some extent, we are saying we are looking not really for big things, we are looking for needles in a haystack. And how to find the needle, can I find it also in this standard machine learning way? I will show you some examples where we had success so far, building maps of materials. And the motivation which I had some years ago was to some extent the periodic table of the elements. When Mendeleev somewhat ordered the atoms which he knew, he looked at the chemistry of the atoms and he looked at the weight. And from this he put these things in some order. When Mendeleev did this, he knew something like 52 different atoms. Now we know more than 100. But doing this and creating a table, he found that there were a lot of elements missing. So gallium, for example, was missing. But he knew that on at this plot, this type of table which he created, there must be an atom, and he even could say what the chemical properties of this atom should be. So putting data in some order is actually very useful, even if Mendeleev did not understand why this order is there. The reason behind the Mendeleev table only came when we knew quantum mechanics, when we had actually the idea that there is a shell structure of electrons around atoms. So starting with finding structure in data or big data is very useful. And in engineering, there's actually what is called Ashby plots, which is somewhat similar to what you see here. So we are looking for crystal structure predictions. We wanted, and I show you this example, zinc blende or rock salt semiconductors. We want to arrange them that I can tell you there is a map, and if I'm in this area, the system will take this structure. Without doing additional calculation, I just want to say, in this area of the descriptors, which we have slowly defined, we find this structure. We have done this in particular for indium, aluminum, gallium oxides, which seems to be a very promising new material for new type of semiconductors. Not yet, I mean, that people can grow this experimentally is only since a few years. We found something for perovskite, this type of table, crystal structure predictions one way. Another thing, and I show you this, is topological insulators. You can build a map where you find, without really having done a calculation anymore, you need of course some results for identifying the map, but then you have this map and you can say in this area, if there is a system, a material, it will be a topological insulator, or it will be a trivial insulator, or it will be a metal or something in between, which I tell you later, and so on. And for catalysis, the same thing. And if I have time, I also really mention very briefly carbon dioxide catalysis. Because in principle, carbon dioxide is something bad if you put it in the air, but it's actually very useful if you do something with this. You can build methane and other fuels out of it. So let me explain the method or the concept in a simple way for a zinc blender and Wurtzite rock salt semiconductors. So if you calculate, so these are two structures. So zinc blende is a structure which you could say is the same structure as you find in silicon or diamond. But zinc blende is more general because there are two different atoms. But in principle, the local structure is the same as silicon and diamond. Every atom is connected with 4 other atoms. So the green atom is connected with 4. This is the zinc blende structure. The same atoms which form zinc blende can in fact also take the rock salt structure, which you see here. And in rock salt, every atom is connected not with 4 neighbors, but with 6 neighbors. And that's why rock salt is very different. Although it's the same chemical formula, it has a very different behavior in materials properties. Can we predict, without doing a calculation, without doing an experiment, if a system assumes this structure or the other structure? If we do the calculation, you have 2 atoms, and you can identify them by nuclear numbers, ZA and ZB, and you can calculate the energies. So full red means zinc blende is clearly favored. A little bit more, less full red or open red means actually zinc blende is only a little bit favored, completely rock salt. Green means the 2 structures have nearly the same energy, and blue means it is really rock salt. If you just do the calculation or the measurement, you get this type of behavior, and you don't see really that this is a simple map. What you want when you talk about a map is you want to bring this structure, which on the left, to something which is in the middle. Then on the left side you have the rock salts, and on the right side you have the zinc blende. like a map about countries, right? I mean, there is this country, and then there's the borderline, there's the other country. And this way you want to really form also maps of materials. But, as I said, how to find these descriptors? If you found the descriptors, the machine learning is more or less trivial, but the physics is in finding these descriptors. This is an old problem. In principle, people have done this before, but in fact, it goes back to Jim van Vechten and J.C. Phillips, but they have created the map, but they have created the map where they included materials properties. So they included the dielectric constant of the material they want to identify. And so in principle, they had a similar spirit, but of course we want descriptors which do not have any information about the material which we want to identify. And of course, there's no reason that this thing is two-dimensional. I mean, we plot it in two-dimension because it's nice to plot, but in principle, actually, there could be also much higher dimensionality when it comes to materials properties for certain things. So here is the idea where I compare what we are doing to find the descriptor, and I said finding the descriptor is the issue, compared to standard kernel-rich regression. So the idea or the wish is to interpolate known data point and to build a function so that this function you can use for interpolation or even to extrapolate. In kernel-rich regression, as we said, usually people use Gaussians. You have a sum over Gaussians, and you somewhat try to optimize or minimize that the difference between the function and the data points which you know that this difference is small. In compressed sensing is what we are favoring. You're doing it in a different way. You say, actually, I don't know the descriptor. I want to find the descriptor out of many, many, many possibilities. I just say this, I just create possibilities and then I try to identify the best descriptor. This is a method which comes from, in terms of mathematical terms, from signal processing. So what you say, I want to represent my function as a scalar product of a vector D, where D has all possibilities which you think could be a physical meaningful descriptor, and some coefficients which you still have to identify. And then we identify that, or require that this P of D and the known data points should be minimized. Now, to do this, you need, in fact, because you have so many parameters, you need a so-called regularization term, which in machine learning usually comes from the fact that when they did this for health or social sciences, they had some noise. Now, we don't have in computational science noise. We have uncertainties, but we don't have really noise. But they added a term like this one, which in fact means that you have all these data points, but you don't want to go exactly through the points. You want a smooth function which goes as close as possible through the points, but is smooth. In compressed sensing, you add actually a term which is a so-called norm zero, a lambda parameter and the norm zero of the C. Now, what is the norm zero? You all know the standard norm, which is the length of a vector. The norm zero is the number of non-zero elements. That means if you have a vector, let's say 1, 1, 0, 0, the norm zero would be 2, because 2 elements are non-zero. Right? So even say 2, 2, 0, 0 would be also the norm zero would be 2. So the value doesn't really matter, the number of non-zero elements. And so you add this thing in the optimization. So you also request that at the same time when these two should be as close as possible, you require that most coefficients should be 0. But you want to increase, you want to decrease the norm 0, and the way to do this means actually that most elements should be 0. This is very difficult to do, at least at bigger dimensions. It's a combinatorial problem because you already have to see actually where the other points are. And so you cannot really do this for many things, but you can do this for systems up to say something like 5,000. So what you can do if you have 5,000 dimensions in this vector D, that means 5,000 possible descriptors, and now you solve these equations you find from these 5,000, maybe only 1 or 2 are really needed. All the other coefficients are 0. And then you have found that 2 descriptors, or 2-dimensional descriptors, is working very well. This was the work which we did initially in 2015, and the method which was used is called LASSO, least absolute shrinking and selection operator. But this method had the problem that, as I said, you can go up to something like 5,000, and if these descriptors which you start with, you have different ideas what could be a descriptor. But some of these ideas may be not completely independent, they may be correlated. And if there are correlations, LASSO actually does not work. So what we have found the last years, in fact by a Chinese postdoc, Runhai Ouyang, is what we now call the CISO thing, which I show you in a moment. And with CISO, you're not limited to 5,000, you're not limited to systems which are not correlated. Correlations does not play a role. You can go to trillions of possibilities. You have a trillion type of possible descriptors, and then you find from the trillion the 1 or 2 which are really relevant. CISO means sure independence screening and sparsifying operator. And as I said, actually 100 billion or actually trillion elements are possible. So when we do this type of approach for our rock salt zinc blende thing, we find that from really a trillion different possibilities of atomic quantities, the CISO finds a descriptor which you see here. Very strange functions, and I would say in the spirit which I mentioned at the very beginning, the function probably does not have a physical meaning. It just identifies the correlation, but the elements which enter, they have a physical meaning. And you see, the best descriptors depend on, I should say what RS is. RS is the radius of the S wave function. The orbital in an atom, of course, is an oscillating thing, and the maximum of this, the last maximum of this orbital, if it's an S orbital, is the S. So the RS is the radius of the S function at the B atom. This is the radius of the P function of the A atom, and so on. So you find actually a very strange equation, but you find what is driving, what is actuating the behavior. And in this way, you see there is a borderline on the left side. Everything is rock salt. On the right side, everything is zinc blende. If you give me a material, these are only atomic quantities. I can tell you if it's living here, it will be zinc blende. If it's living on the other side, it will be rock salt. Very interesting. There are 2 things which are pretty far away. I mean, most things are in this region here, but there are 2 elements or two materials which are far away: boron nitride and diamond. And so we did the same thing in saying, let's do the learning without any information of boron, nitrogen, and carbon. And the nice thing is this system would have predicted that these systems are particularly stable with respect to their cohesive energies. The distance to the green line is the cohesive energy in this case. So if diamond would not have existed, the leading author would be very famous. But of course, that was been known before. But it just shows you that it's even really predictive if you do it this way. And I give you another example, which is now the topological insulators or spin Hall quantum systems or insulators. A standard semiconductor, as the one which we just have discussed, has a valence band, it has a band gap, and then the conduction band. And typically, the valence band is built from certain type of orbitals. Let's say if it's a zinc blend, or let's say it's gallium arsenide, you could say the valence band is coming from arsenic orbitals, and then the conduction band from gallium orbitals. So they're very different type of the wave function character. This is a trivial insulator which is known since many, many years and used. But in principle, there are mechanisms in the many-body Hamiltonian that you can make this band gap smaller and that you can bring it to a type of inversion. And so the axis here typically is spin orbit coupling or alloying or strain or electric fields. So of course, in theory, you can play with spin orbit coupling. In an experiment, you cannot. You have to replace atoms by another one. But in principle, you come from from a situation which is a standard semiconductor to a situation where the top of the valence band is already red, that means from conduction band-like, and the bottom of the conduction band is already blue, that means valence band-like. Now why is that interesting? It's interesting because it means that these bands, the valence and the conduction band, are connected by essentially straight lines, at least straight lines in the middle, where one is can only hold electrons with spin up and the other one with spin down. However, in this system, these state lines actually cannot live because these are states which have an imaginary part in the energy. They would have actually an increasing amplitude wave function, but they can live at the surface. So for example, if you have a two-dimensional system like graphene or some other two-dimensional system, there is none of these green states in the middle, but at the edges there is in fact a surface state which behaves like the states which are plotted here. The interesting thing is that these states, because they have a different spin, which goes with the time reversal symmetry, means the following, that if there is an electron at the edge of the system and this travels in this direction, this electron, if there is a perturbation, cannot scatter back. Backscattering means resistance. So that means electrons travel without resistance. And they cannot travel back because the only Fermi level is to also change the spin. So if you stay in the same spin channel, if you don't really allow for spin changes, there is no resistance in these systems. So that is actually very interesting, and these systems have been identified in various experiments. I should say, many years before they have been identified, they have been discussed in some Russian paper, which has been ignored to some extent, Volkov and Pankratov. Everything which I've said here was actually said in this paper by Volkov and Pankratov in '85, except one word. The word topology is not in the paper. So they say actually why this happens, but they didn't really say it's a topological insulator. They said actually it's an insulator with these and these properties, and that's why it was really forgotten when this field of topological insulators became actually very fashionable. So we have done a lot of work on this, looking at two-dimensional systems which are AB compounds, which are functionalized with some other systems. So AB, let me actually show the structure. So it's really a hexagon, it's two-dimensional. It's which you don't see because, let's actually, the side view is here. So we have a red atom, a blue atom, a red atom, a blue atom. So it's a two-dimensional system, hexagonal, but above the blue atom is a black atom, and below the red atom is also a black atom. Basically, it means if it's graphite or graphene, stable from carbon, you have carbon, and then you have any of these gray atoms could be on top or below, or you have boron nitride, and you have any of these gray atoms. Any of these combinations which you can build up are investigated. And of course, not any are investigated. We investigated 222 materials, and then we looked, and CISO told us from the data there is structure. And so CISO told us there is structure, which again, these coordinates, which we didn't know before. So there is a ZA and ZB enters, there is the highest occupied level which enters, there's the electron affinity which enters, and you see in this direction you don't need actually the X, whatever you put on top, it doesn't really matter. It goes from metal to a red thing, which I say in a moment, to this functionalization independent topological insulator. So in these atomic quantities, everything here we predict will be a topological insulator. Now if you then see here, it doesn't really matter what X you put on top. It's function independent, but of course there is a region where it depends in what you put on top and below. So they are functional dependent topological insulators. This is something which has not been expected when we did these calculations. And of course, there's a region where things are just metals, and there's a region where things are just trivial insulators. So from calculating some things and then asking what is really driving the behavior, we find this map of materials. We find descriptors which only depend on 3 atoms. And we find materials which do not follow the rules, namely that sometimes it depends on what you put on top or below, and the reason mainly is that it really depends what structure the systems take. I think actually I'm running a little bit out of time, so let me actually just jump over this. I wanted to go briefly on carbon dioxide work, but I'm just actually going, I think, better to the end. And let me see. So where is the end? So actually there are 3 or 4 slides at the end. So what I wanted to show you is, so this is the structure of this NOMAD laboratory. The amount of different materials which you could imagine is huge. So we already know that 200,000 inorganic materials exist. There are many more organic possibilities, but 200,000 inorganic materials exist. But for most of these inorganic materials, we don't know, in fact, their properties. We don't know if they are metals or semiconductors. We don't know if they are transparent. We don't know really what they are. But then if you think about more, what you can do with these atoms of the periodic table, the possibility, if you include also nanostructures and surfaces and heterostructures, the space of different materials is certainly not 200,000, is practically infinite. So there's many, many more materials which exist, and if you plot these maps, then we may actually find something which is even better working than what we are using today. But the important thing is the number of materials that exhibit a certain function is rather small. If you want something which is transparent, which has the best transparency, which has the highest heat conductivity, already it's actually only diamond which is actually having these properties. So it's very few elements which have actually certain functions, and so what we are looking is more like needles in a haystack. This is actually what I just was jumping over. The space of chemical and structural component is very sparsely populated, and that's why the sparsity is important. That's why these methods like compressed sensing, which in fact exploits the sparsity, is so important. Nearly everyone is talking about big data analytics in material science, and with every new idea, with every new technology or new science, the importance, so what I plot on this thing is the importance of a new technology, the relevance. How relevant is that? So people always think actually with machine learning you can actually solve every problem, and you're getting actually on this standard learning curve here. This is where, in fact, the learning is. But where is the reality? And the reality, in fact, is more here. The perception, this is the reality. But the perception, what people believe, how important it is. So I think at the moment we are probably at this point in machine learning or artificial intelligence. We are still actually on a learning curve, and there are still a lot of things to learn. But when people talk about it, what they think how important it is, they think it's already extremely important, and they think it's important that something which we will probably reach in something like 4 or 5 years. So perception or hype is much higher than the truth, but I think the potential is certainly very, very high. I wanted to finish with the website of our laboratory and a little movie or video. Has the largest repository for input and output files, and from the open access data there are certain big data services. We have a data analytics toolkit which helps you in basically what I showed you to do yourself. Data is a crucial material of the first century, and this is now in this YouTube or UQ movie, and I want to show you this in 3 minutes, and then I'm nearly finished. I hope.
NOMAD European Centre of Excellence, your gateway to material science data. This is John, an who wants to build the best solar cells ever. And this is Laura, a chemistry researcher who wants to design the most efficient batteries for the next generation of electric cars. So what do John and Laura have in common? Well, to achieve their objectives, they both need to use new high-performance materials. So what can material science do for them? The ideal solution would be to provide them with a map of materials where they can identify and select what they need. Indeed, the amount of different possible materials is practically infinite. So what if all materials could be grouped according to their properties and functions? Is this already possible? Well, this is the idea behind NOMAD, the Novel Materials Discovery Laboratory. NOMAD is the European Centre of Excellence in Material Science Data, set up in 2015 to enable the quest for new and novel materials and their properties, and to reveal unknown properties of already known materials. The foundation of this European Centre of Excellence is the database called the NOMAD Repository, which is available to all and based on open access principles. It hosts input and output files of all significant computational material science codes for at least 10 years, for free. It also enables a confirmatory analysis of materials data, their reuse and repurposing. As the NOMAD repository includes extremely heterogeneous data, which do not allow for direct comparison, these are being processed into code-independent, machine-readable, and standard form. This is the NOMAD archive, which provides the open access data from the repository in an easy-to-use and easy-to-access way. The archive is the base for the NOMAD encyclopedia, which displays the properties of computed materials based on millions of calculations that have been performed worldwide. Not only does the encyclopedia provide information about known compounds and their known properties, but it also makes it possible to propose a previously unknown material with the desired characteristics for a special application, or to bring to light the previously unknown properties of known materials. The NOMAD COE also provides a set of big data analytics tools that uncover structure and correlations in big data of materials. This enables scientists and engineers to decide which materials are useful for specific applications, or which new materials should be the focus of future studies. As seeing helps understanding, NOMAD is also developing a virtual reality environment to allow for interactive data exploration, training, and dissemination. Clearly, all of this is made possible by the underlying NOMAD high-performance computing platform, which consists of a distributed multi-layered storage system connected to a scalable computing capacity. Data is the raw material of the 21st century. If you deal with material science, the NOMAD Centre of Excellence is your gateway. Start using it now at nomad-coe.eu.
So, as we said before, we need extensive sharing of data. That is the NOMAD or FAIR principle. Data must be findable, accessible, interoperable, and repurposable. This is where we see the transition really happening over the last 2 or 3 years, that more and more people worldwide are doing this. It helps, I think, significantly to speed up science. And of course, when data are fair, in this sense, they can be used for artificial intelligent approaches. And only then they can be used for that. And of course, this is what we want to do. We not just want to store and create data, we want to do science with the data. Now let me finish in saying that we have a fantastic collaboration here with people as USGC. In principle, and mainly, I would say it's Ren Chingu, who's already standing up, Li Weishu, and actually also Li Xin. But all this, as you have also seen, can only work if very close and good connection with computer centers. And I think there, Li Ximin is really helping significantly on this. And with this, I thank you very much for your attention.
Thank you very much for this very interesting talk. Now there are time for questions in the comments.
Please.